from LIGENTEC in Switzerland, who, well, you already saw an introduction to LIGENTEC in the sponsor videos, but Dr. Geiselmann will give us a lot more information about LIGENTEC's silicon nitride photonics technology. Please.
Thank you very much, Wim, and thank you very much the organizers for inviting me here. We have already seen this morning in the keynotes that silicon nitride has some key advantages, and I would like to go into these details. So LIGENTEC is offering a silicon nitride versatile platform, and especially for low loss photonic integrated circuits. We are an independent Swiss company with worldwide customer base, including Chinese customers, and have prototype and volume capabilities on 200 millimeters. Let's start with why are losses important. We have already seen some applications, and we'll see more applications afterwards. For example, LiDAR has long delay lines that needs tens of centimeters of real estate on the chip, where propagation losses are important. The photons that you want to detect that are coming back, you don't want any photons to be lost because of propagation losses. And phase noise in FMCW is related to losses. So the better the losses, the better the signal. In telecom and datacom, especially for CWDMs or using AWGs or other architectures to do CWDM or DWDM, you're very sensitive to phase noise, which is related to the loss of a waveguide. That tunable lasers is also related to losses. You can do very narrow line width lasers if you have very low propagation losses, and you can have very narrow bandwidth filters with very low propagation losses. For quantum computing or neuromorphic computing, you have many times asymmetric Mach-Zehnder interferometer trees or high-Q resonators that are again very critical to low loss propagation. So where do these losses come from? We have absorption loss that annihilate photons in materials, and here we're using low loss LPCVD silicon nitride that gives very good performance in the material. We have scattering losses due to surface roughness, so we need to take care of a very good surface roughness. This is how it shouldn't look like, and this is also a mountain here that was the surface roughness was done by a glacier. And radiation loss. So if you do very narrow bands, then you have radiation loss, which we also need to take care of. So this is why we are proposing to use LPCVD silicon nitride with a very high confinement, where you can avoid having seeing the surface roughness or much of the surface roughness. You can do very small footprint because the waveguide is guiding the light very well, and so you have very low radiation loss. Just to put that in a figure, in that paper, they compared like the minimum bends that you can do with fibers. You're in the range of centimeters to meters. If you go to a low confinement silicon nitride platform, you're still in the range of centimeters. But if you go to a high confinement silicon nitride platform, then you have bend radiuses that are in the tens of microns that are possible. Another source of losses is actually the coupling to from fibers to the chip. And here we have engineered an edge coupling with a spot size converter that fits the mode field diameter of an SMF 28 fiber to minimize coupling losses already at the edge of the chip. Similar to that, we also have the capability to engineer spot sizes if you want to couple a laser or some other get a certain mode shape of your choice. You can engineer that in the platform. So with this morning, we already have seen that silicon photonics is covering a bunch of applications, but with all these other applications in the visible and the losses, silicon nitride gives a good complement or even the only choice, depending on which wavelength operation you are or how much loss you need in terms of propagation loss. So we have seen many of these applications. We will also see more applications later on. They need large transparency windows, low propagation loss, and especially for LiDAR, also high optical power propagation, where you do not have any to photon absorption that you have in silicon. Additionally, you need the scaling to volume, which is possible, which is given with silicon nitride. So our offering is to have this very low propagation loss with very low coupling loss, with a fast turnaround time, and the platform for heterogeneous integration. We offer 3 standard thicknesses of silicon nitride, and any kind of custom thickness is available for dedicated runs. We have more than 10 process modules that include different thicknesses of silicon nitride, different shapes of the silicon nitride, openings of the cladding, stacks, multiple stacks of silicon nitride, where you can propagate them in several layers. And this comes with an extensive PDK, where we have implemented design rule checks, building blocks such as these Mach-10 interferometers, AWGs, ring resonators, and the optical coupling. And the design flow is implemented with commercial software houses that so you have no problem in designing and simulating your layout. And just to give an example, what that means, that PDK and the understanding of the platform, using these commercial software tools, you can simulate. And in this case, we'll see simulated here a 72-28 percent MMI splitter, and when we measured that at 1550 nanometer, we got 70.8% and 29.2%. So that gives a very good overlap of the simulation and the fabrication capability, and the guarantee that we understand very well our platform. I mentioned the heterogeneous integration, and this is one thing that we need in terms of photonic integrated circuit offering, because silicon nitride is intrinsically a passive material, so you need to integrate active components. And here we have developed a module where you go from the silicon nitride, you have all the advantages of the low propagation loss in the silicon nitride, and then you go to lithium niobate, indium phosphide, or any other material that you coupled the lights to, and do only the necessary action in either laser generation, laser light generation, modulation, or detection on these materials, and have the silicon nitride circuit to propagate your light in a very small chip size and with very low propagation loss. With that, I will show some examples from different application areas, and start with communications. Here we have already seen this morning that the silicon nitride is a very good candidate to have low temperature dependence, good process tolerance, and scalable. And we put on top of that the high confinement to have very low phase errors and this very small footprint. So we can in our platform even design AWGs that are polarization independent, that can be used for TE and TM polarization. In this paper here, they showed by using our platform that you can get very low insertion loss with the Gaussian AWG, insertion losses below 0.5 dB, and crosstalk levels of minus 35 dB, with standard deviations around 0.5 nanometers. And you see the size of that is quite small on the chip. So the temperature dependence is because the dN over dt of silicon nitride is 10 times larger than the silicon photonics, and this is why when applying temperature you only get small shifts, and you can do athermal designs in silicon nitride. You can also do polarization management in silicon nitride. Here showing a polarization splitter. We can also do a polarization rotation in silicon nitride by using the different process modules that I have presented in the beginning. LiDAR will play a key role in photonic integration, and especially FMCW LiDAR is at the moment one of the most promising LiDAR techniques that will make it. And here the key requirements are that you need high power propagation. So you need a lot of light that goes out and detect a few photons that come back. You need low loss propagation, low phase errors, and low crosstalk between your different detection channels. So here the high confinement with long and low loss delay lines is very promising to help solve the problems for FMCW LiDAR. Another way of doing LiDAR is phased arrays, what we have already also seen this morning. Here you need to put many emitters that form your phase front in the end. So you need to have a very dense array of the emitters. You need to control the numerical aperture of your phased array, and you need a high phase stability, which again is related to propagation losses. If you have very high propagation losses, you get phase instability. And first phase arrays have been shown here in our platform. Switching a bit to sensing this and microscopy. This is, I believe we will hear much more about that in the talk afterwards from Laura Lechuga, but just to give a brief overview what you can do with silicon nitride here, because it's in the visible range up to the mid-infrared. So you can open sensing windows that you have your evanescent field interacting with any kind of a virus or gas or anything that you want to detect. That gives you then a shift in either in the resonance of a ring resonator or in the dip of a Mach-10 interferometer. You can also do that you can also use silicon nitride for microscopy, where you use the pick to guide your light to the sample where you want to illuminate that, and that has been shown in that paper here, where they illuminated here biological structures. Another way where silicon nitride needs to be needs to be used over silicon is all the wavelength range from 400 to 1 micron. And here you can imagine that by implementing, for example, an array of AWGs, you can do an integrated spectrometer also in these wavelength ranges. Another very promising application for silicon nitride is quantum computing, where you have again you need very low loss propagation. Every photon counts because you generate these quantum states on the chip, and if you lose photons, then that means that you lose one of your qubit. You need a very high phase stability, and that means that integration is on-chip integration is needed to have no movable parts. You need very small size components that you can integrate everything on the chip, and you need the wafer technology to be able to scale to high volumes. And in like that Canadian company Xanadu has shown on our platform that they have generated 4 squeezed states here, so 4 qubits, filtered that, and then did the calculation, the quantum calculation in that interferometer array, and like that they showed different quantum algorithms that are possible on a silicon nitride pick. And one quantum algorithm that they did is that they calculated the vibronic spectra of a molecule with that quantum computer based on our chip. Last but not least, I would like to mention metrology, and here it's similar to the squeezed states. How you use a high Q resonator with a CW pump light In that high-Q resonator, you get a Chi3 nonlinearity because of the silicon nitride, and can have four-wave mixing that spans out a so-called frequency comp, and that is dependent on the dispersion that you choose for the high-Q cavity, and that is you're able to tune the dispersion by adjusting the width of your resonator. And like that, for example, you can generate such a nice spectrum here of a frequency comp, and can use that for several areas. There has been many different applications proposed for frequency comp, and one of that was recently shown is low noise microwave generation. So there is a whole bunch of different applications and areas that need silicon nitride, and that where the high confinement silicon nitride that LIGENTEC is offering gives tremendous advantages. And I don't go more in detail. You have here a publication list on our website if you are interested in reading on those. So how can you partner with us? So we have initial contacts to concept and designs with a strong partner network. We have prototyping capabilities and pilots to volume fabrication capabilities for large volumes and high capacity wafer fab and fully automated testing. We offer these so-called multi-project wafer runs every 3 months, where you can jump on and do a first prototyping before going into volume fabrication. With that, I would like to close here with an overview what I've shown. So the LIGENTEC silicon nitride provides a very high mode confinement with very low propagation losses that enables a very small footprint of the PIC and allows high power propagation. In terms of active elements, you have electrical tuning through heaters and modulators, lasers, and detectors through heterogeneous integration. The PDK that we have developed gives you a whole suite of components that you can use to lay out your circuit. And we know that it's very important to have the weld connections to the optical fibers, to have a good coupling of the light from the fiber to the chip, and we offer various solutions here. With that, I would like to thank again the organizers and you for attending this symposium.
Thank you, Michael. Okay, are there any questions? I see there was one question posted in the chat by Nanye. How about the roughness of the surface for the thin silicon dioxide cladding after dry etching and wet etching?
Let me see. How about the roughness of the surface? So the roughness of the probably what you're referring to is this one here, the roughness of the surface for the thin cladding after. So here the surface roughness of the the nitride is not affected by that process step. If that is the question.
There's another question also now posted in the chat. People, please use the Q&A box instead of the chat for posting questions. But okay, I'll read it here. It's a question by Shin Gong, who unfortunately missed part of the presentation. But he asked if there's any example for fiber sensing interrogators or OCT.
We have a few examples, but I haven't shown any example here. So if you want to contact us, then I can send you a few examples for that.
I also have an additional question. So now you're showing your infrared and your visible light platform, at least that's being offered as MPWs. But how do you see the proliferation of new custom layer stacks and platforms? Do you think basically for most applications people will need a custom platform, or will you really have like one or two platforms or one or two standardized platforms that could handle most things?
So mostly we believe that with one or two standard platforms you can address most of the customers. Then that being said, if there is a custom thickness that is needed for one customer that needs to go to volume, then there is always a way to develop that custom thickness also for volume. I say volume here because for prototyping, a custom thickness is probably easier handled than for volume customers. But if there is a drive behind that, then that is definitely implementable. Yeah. But first we will obviously check if it's easier to implement it in one of the existing platforms.
There's one other question in the chat or in the Q&A, but we have to move on. So I would suggest you answer it offline by typing the answer in the Q&A box, and
yes,
we will proceed to the next speaker now.
Thank you very much.
Michael, it was a very, very enlightening talk.